All right, we're gonna do the course schedule problem using a depth first search. Last time, if you saw my last video, I did it using using Con's algorithm. But this is your first time seeing this problem. Anyway, they give us two things. They give us the number of courses and they give us some prereqs. They just want us to return true if we can take all the courses. The only reason we wouldn't be able to take all the courses is if there's a cycle in this graph of edges that they give us. Which would mean that there's at least two courses that are prereqs of each other, which means that it's impossible to take either course, right? So anyway, we're going to do depth first search, and in a depth first search, the way you check for a cycle is, so we detect cycle in DFS and or depth first search if we've seen a node again in our recursion stack. So basically, in depth first search, while we're recursing, if we encounter a node again, like if we encounter it twice, then we have a cycle in our graph, because it should be impossible. If there's no cycle, it should be impossible to see the same node twice while we're recursing down our graph, because our graph should be acyclic, right? Okay, so let's actually write out. Oh, so first, we got to convert this prereqs, this int array, whatever, we got to convert it to an adjacency list because we want to be able to easily loop through our neighbors in the depth first search. So let's create a map of integers to a list of integers. It's just an adjacency list. New hash map. Cool. And we're going to loop through our prereqs. Just call this edge. And prerequisites. Okay, can't spell. And we want to start populating this adjacency list. So we're going to use compute if absent, and I'll explain why I'm using this method in a second. So first, if we haven't seen this key before, what we're going to do is we're going to create an array list, and then we're going to add the neighboring node. And if we have seen this key before, it'll just return the array list that we created in a previous iteration of the loop. Okay, so now, before we start our depth first search or our DFS, we need a couple things. We need a visited array, or a set of visited nodes. So let me create that, new hash set. Okay, and we need to keep track of the nodes that we've seen in our recursion, or the recursion stack, however you want to say it. So we're going to use a set again, and we're just going to call this stack nodes. Let's go with stack nodes. No, let's just go with stack. I know this is like a weird, I don't really know what a good variable name is for this. I guess it's stack nodes, but this is essentially going to hold the nodes that we've seen while we're recursing in our recursion stack. Even though we're using a set here, I don't really know what a better name for that would be. But anyway, now we want to loop through all of the nodes in our graph. So, so in the adjacency list, we want to loop through all the nodes and check if any of them have a cycle. So if, or for every node in the adjacency list key set, this is all the nodes. If that node has a cycle, and we need to pass in, or let me just finish this. So if it has a cycle, we just return false, right? And if none of those nodes had a cycle, then we just return true because there's no cycle in our graph. But we need to pass in a few more things into this has cycle method. So we need to pass in the adjacency list. We need to pass in the visited and the stack. Okay. And now we can go ahead and copy paste this and actually write out our DFS method. So this has cycle is going to be the DFS method. So let me type that out really quick. And we need to give these types. So node, this is just going to be some integer. It's adjacency list. It's up here. Let's copy paste that. And let's put this on another line. Make it nice. And we just need set of integers and a set of, and this is the nodes that we've seen in this recursion stack so far. Okay. So first we're going to check if we've seen this node before. If we've seen this node before in this recursion stack, that means we have a cycle. So if stack.contains the node, then turn true. It has a turn true because that means that it has a cycle. And if we've already visited this node, but like for example, it's possible to visit this node without it appearing in this recursion stack because we're doing a depth first search from every node in our graph. We're starting a depth first search from every node in the graph. So if we, for example, let's just say that on the first node we call our has cycle method, and we're gonna populate some nodes into this visited set. Well, we don't need to go through any nodes that we visited before in some other DFS path, because if there was a cycle in that path, then that first call to hit has cycle, or that first depth first search path would have detected the cycle already. So we don't need to like recheck any nodes that we've already visited. So we can just check, say if this is just an optimization really. So if visited dot contains the node, return false. And we can return false because this means that we've seen this, we've gone through this path before and there was no cycle. And if there was a cycle, we would have returned true at some point. So anyway, what's next? So we need to then depth first search through all of our neighbors. So for int, say for every integer neighbor in the adjacency list, get the node, then want to check if that has a cycle. So if has cycle, or yeah, so if has cycle, again, we would return true here. And we're going to pass in the neighbor, pass in the adjacency list, pass in the visited, and pass in the stack. And we want to return false if we didn't detect the cycle. And we need, before we do all of this, we actually need to populate our stack and our visited. I forgot to do that. So really quick, we're going to do, we're going to add this node to our recursion stack. So stack.push, or no, this is a set. So we're going to do stack.add the node. And then we're going to do the same thing for visited. Add the node. And then we have to remove this node from our recursion stack after we're done. Once we pop off of this, like, because this is recursion, right? Once we pop off the stack, we want to remove this node from our recursion stack. So we're going to just say remove. Okay. So I think this works. Let me see. Let's try this. What am I? Oh, I'm missing a thing. And I'm missing a semicolon. What else am I missing? Oh, it's because I copied and pasted and I'm missing another arrow. And what? How can this be null? This shouldn't, because I'm going through the key set. What? Cannot invoke iterator because the return value of, oh, because when I'm going through the neighbors, okay, so we need to, okay, my bad. So when we're going through the neighbors, so the very first recursion, so the very first call to has cycle from up here, this will never return null, right? Because I'm going through the key set here, so I'm guaranteed that this key exists in that adjacency list. But when I'm going to the neighbors, those neighbors might not have edges to other nodes, so I need to check if the adjacency list even has that key, or if it has the node. Okay, so all I'm checking is does the adjacency list have this node, and if it does, then go through the neighbors. Okay, so that was a little oversight. Okay, cool. Submit it. All right, so it works, and this is how you check if there's a cycle on a using depth first search. All right, so the time complexity is going to be O of V plus E because of the the depth first search, and then the space complexity is going to be O of E because of our adjacency list that we populated. As for the recursion in terms of space, this is never going to be bigger than the number of the number of recursive calls can't possibly be bigger than the number of edges, right? So at the end of the day, it ends up being O of E is like our biggest factor. So yeah, if you like the video, you can give it a thumbs up, and yeah, you can subscribe if you want. Cool, bye.